Okay. Hey, welcome to first actual lecture of the course entitled Simulation of Mechatronic Machine. And you see that there's a little bit of hassle here, and the hassle is because of the green screen that I'm using. The green screen was actually a problem a week ago, or let me put it another way around. So it was a problem that we were not using the green screen. Instead, we were using a software-based green screen. And obviously, my laptop was not powerful enough to do all the computing. That's why it was breaking all the time. And it wasn't about the cable connection. I am today cable connected, and I really hope that everything works fine because I have some important information that I would like to share with you. And that's all related to simulation of a mechatronic machine. Okay, so guys, you ready to go? Very good. Okay, so what I will do then is that let me get started from the beginning. So I started a week ago by explaining what is a multibody system. So let me refresh your mind about what is a multibody system, and then what happens then is that we will take a big picture. How is that we can describe rigid bodies in planar case? Planar means two-dimensional space. How is that we can do that description? This is an information that is extremely important you to understand because we will use that description, which is called kinematics, over and over and over again. So if you get lost today, raise your hand and say, hey, Aki, you're not clear enough, so can you please repeat? And I will do it. By the way, let me set the competition. So the first student raising a hand and saying, Aki, you're not clear enough, you need to repeat it. I'm going to offer you a cup of coffee. Deal? Usually I carry those coffee coupons with me. By the end of the lecture, when it is roughly a Christmas time, I use that coffee by myself because you never ever say, Aki, you're not clear enough, for the reason which I don't understand. Am I clear enough? Okay, very good. Okay, description of rigid bodies. That's what we're going to do today. And velocity and acceleration. Very mechanical thing because description of mechanical or rigid bodies is about the kinematics. Once you know the kinematics, everything after that is mechanical. It's just a pure mathematics. From position, once you know the kinematic position, you can get the velocity by differentiating position with respect to time. That's math. So it's not very complicated at all. Acceleration, you differentiate the velocity one more time with respect to time, you will get an acceleration. We will do that all, but we also take a look at what that means for us, what that stands for us. What is a physical interpretation of whatever we will get? And that's pretty much how we're going to go when we look at the equation of motion as well. Now keep in mind that this week and 2 more weeks from now, we will not discuss about forces. We only discuss about how you can describe something, how you can describe particles, how you can describe bodies, how you can describe joints. So we don't discuss about forces. And when we do not discuss about forces, it is not a dynamics, but it is kinematics. Kinematics is a science and art of motion, science of art. The art part is what we're going to do today. We're going to set how you can describe rigid bodies. Science is this mechanical mathematics, how you differentiate the position with respect to time and so on and so forth. Dynamics is a different story. Then we need to look at the forces. How is that we can find an equilibrium of forces? Basically, we have 2 different kinds of forces, external applied forces and inertial forces. Inertial forces is a mass multiplied by acceleration. Not too complicated. And that all you know already. You learned that already in, elementary school, 100 years ago, 20 years ago, 10 years ago, 15 years ago, something like that. So that all you learned already a while ago. Okay, let me get started with this. So multibody system dynamics. What is a multibody system? So multibody system, as the title implies, is a system that consists of multiple bodies. But there is another requirements that the multi-body system have to fulfill. And that's the requirement that the bodies have to be connected together via joints. Joints are the ones that are limiting the motion possibilities between the neighboring bodies. Crankshaft mechanism is a good example. Connection rod is not able to move as it wants, but according to crankshaft and a piston. So it's connecting to these two bodies together, and it has to do this connection job all the time. So it cannot take a leave and go someplace else. That's not possible because it's connected to neighboring bodies. Those ones are called joints, which mathematically we're going to describe by relating the motion possibilities between the neighboring bodies. All sounds like but all becomes to be clear when we look at that in a mathematical level. That's going to be 2 weeks from now. All right. So then also the thing we don't do in multibody system dynamics is that we do not make any assumption regarding the magnitude of rotation. Kind of the simple thing, but it's not. Because if we are not going to limit ourselves to small rotations, it means that our kinematics is going to be nonlinear, and our equation of motion will be nonlinear. That has a serious consequences to our life. And the consequence is the fact that there is no analytical solutions available. This is a clear difference when you're comparing this class to classes you've been participating earlier. Dynamic 1 and Dynamic 2, you always find this analytical solution. Here you don't. You will not. Because you're going to face the nonlinear equation of motion. Because the large rotation. So large rotation requires to use trigonometric functions, cosine and sine, which are nonlinear. All right. Now, robotic system, is that a multi-body system? Yes, it is. Components and the bodies are connected together via revolute joints. So it's a clear example about multi-body system. Windshield, wipers, multi-body system. Excavator, multi-body system. Biomechanical system, me, multi-body system. As with an assumption, because the human joints are pretty complicated. And if I say my knee is a revolute joint, it's not exactly a revolute joint, but it's close to it. So if I make an assumption that there's a revolute joint, most of the studies, that's okay. So I am a multi-body system in a single body, but multiple moving components that way. All right. So a week ago, I asked, what is not the multi-body system? I don't want to jeopardize streaming today, so this Socrative is already on. Go ahead and place your answer again, because you could get extra points if you do so. So if you discuss this with your fellow students, very good, because the one only out of the 4 is not a multi-body system. All right, alternatives are a house as a building. All right, then the B 4-bar mechanism. C is an excavator, and D is an Elvis as a biomechanical system. All right, and I will get back to the Socrative results a bit later. So I will leave you to think about this, not just think, but enter your answer. All right. What is the success rate today? What is the success rate? How many of you will enter correct answer? Is it going to be 100%, 50%, 10%? Statistically, is it 25%? 92. Okay, the online participants too. We got 53 online participants, and I'm sure they're all very happy. Are they? They're not giving any comments whatsoever. Okay. Anyway, so online participants too, place the number to chat window, and if you guess this correctly, you can get 2 extra points. And the numbers are coming now. 94. We get back to the right number a bit later. So let me continue then. All right. Here comes the big picture. This is something that you must understand very well. Okay. In dynamics, we monitoring situation with respect a coordinate system which is called a reference coordinate system. Often you have heard about global coordinate system. Yes, that's a reference coordinate system. It has many names, but it's a coordinate system that everything is computed with respect to it. So that's a reference coordinate system. I can set the reference coordinate system to this table, and I can do all kind of motion with respect to that coordinate system. It's not absolute, because there is always a motion. If nothing else, Earth is moving around. And because Earth is moving around, it is a relative coordinate system and it's a reference coordinate system for me. All right, so then with respect to reference coordinate system, guys, would you prefer to call it a global coordinate system? Is this something that you're more familiar with? Reference is okay, all right? So then with respect to reference coordinate system, we have a multibody system. That's that mechanism we just described. So it could be this connection rod system or crankshaft mechanism, and it consists of number of bodies. These bodies are connected together via joints, as you see here. These are the joints. There are different kind of motion limitation: revolute joint, translational joint, screw joints, combination of this and that. So there's many different varieties, all right? But they're limiting the motion possibilities. So that altogether is a multi-body system. But if you look at the single body consists of infinite number of uniformly distributed particles. What is this particle? How you can see the particles? You do not see it. It's a very small dot, mathematical thing. It's not real, but it's something that helps us to describe bodies. All right, very, very small dots. Because it's so small. It's this small. It's so small that you don't even see it well. Because it's so small, it do not have rotational degrees of freedom, which is really great. Helps us a lot. So when you look at the particle, no rotational degrees of freedom. Because if this small dot is here or here, having this and this rotation makes no change or makes no difference. Rotation is immaterial, if you want to say that in a fancy way. Okay, so that's what we wanted to do. Well, this is the kind of the tree structure of dynamics. Our target here, what we wanted to do, is simple. So we want to describe these particles with respect to reference coordinate system. That's what we need to do. So it's not very complicated at all, because just translational degrees of freedom. Nothing else is needed. No hands up. You know, the coffee coupons and everything. If you raise a hand and say, Aki, I don't understand, can you be more clear? Offer is in a table. Okay? Here it is. Here is my body A. So this is my body. Even though that this consists of infinite number of particles. Today we're going to look just at 3 of them. Remember that in reality there is much more than that. Millions, billions, trillions of particles. But let's, as an example, let's look at 3 of them to make our life easier. So remember, what is our target? Our target is to describe these particles with respect to this reference coordinate system. Well, this is not very complicated at all. So how we can do that? So we can say that there's a vector leaving from the origin of the body. It could be reference coordinate system and ending to be whatever particle is located at. Okay, very simple. So I can do that. And if I do that for each of these 3 particles, it looks like this. Not very complicated at all. So if I look what is this vector is consisting of. So this vector, obviously, because this is a planar 2-dimensional space, consists of how many components? Vector consists of 3, 7. What was that? 3. Correct. 2 components. because in a planar case, vector that starts here, ends here, has a projection in a global x and y coordinate axis. These projections are the components of this vector. All right? So this vector here, okay, I need to bend a little bit to do this writing, is a Rx, Ry. These are projection. Rx is this projection. That's Rx. And this is Ry. All right, so pretty simple thing. So what about this guy here? How many components? 7? 2. Oh yeah, 2. Correct, 2. Because no difference. So these two consist of 2 components. What are these components? Rx, Ry. So it's no difference in that respect. Okay, what about this one? Same thing. So that's going to be another 2 components. So now when I have 3 particles, I need to use 6 variables. Where these 6 variables are coming from? Well, because this particle here can move here, and when you're doing that, then these projections are changing their numerical values. All right. So it's meaning that these particles have to be described by 2 variables, Rx and Ry. Same holds for this guy and this guy. So it means that I need to use 6 variables. It's kind of still doable, but remember the problem here is that how many particles I have in total? Infinite. So this is no go. This is not possible because no computer can solve infinite number of variables. They just cannot. It has to be simplified or described another way. Otherwise, computers will say, hey, this is too much computing for me. And we're still speaking about one single body. And we would like to have them more than just one. Okay? What is that we can do then? Maybe we can use the fact that particles cannot move with respect to each other if we're dealing with the rigid bodies. We're dealing with the rigid bodies. Rigid body means that no matter how force is imposing the body, there's no mechanical deformation. Of course, you don't see that in a real life. Like this pen is pretty rigid, but I can take a big force, very big force, and it will bend for sure. Okay, I'm not going to demonstrate that, but you trust that it will happen. All right, so that's what happens in a real life. But we are not here in a real life. We are here in a computational world. And in this computational world, we are saying that this is rigid. We're making an assumption that this is rigid. That means that the particles cannot move with respect to each other. They just cannot. What that means for us. So it means that this distance between these 2 particles remains constant. So it's not changing when the body is translating or rotating. So it's a constant value. All right? Okay, maybe we can use that and introduce second coordinate system. The second coordinate system is called body reference coordinate system. What is the deal with this body reference coordinate system? Well, it is a coordinate system that is attached to body. So if the body moves, coordinate system moves along. If the body rotates, it rotates along. So it's completely stamped, welded, attached, however you want to call it, to body. So there is no possibilities particles to move with respect to body reference coordinate system. That's very good, because then we can describe each one of these particles with respect to this new coordinate system. We can make it happen. And we can do that by using something that is a constant vector. Constant vector that will be called as a vector U bar. Vector U bar. Bar, in my notation, stands for local coordinate description. And if there's no bar, it means that it's with the reference coordinate system. All right? And of course, if it is bold font, it means that it's either vector or a matrix. Scalars are written using italic font. Okay, so let me take a look. So we have this situation that these particles we looked a little while ago are now described with respect to this new coordinate system using these vectors u bar a1, u bar a2, u bar a3, and these are constant. So we halfway done, more than a halfway done, because what we need to do then is that we just need to relate this description of local coordinate system to reference coordinate system, global coordinate system. All right? Okay, let's stop here. Is it like yes? Or a little bit confused? Or it's like, no way. Okay, we do what? It's like, yes. You do it because your fellow student is doing that. Or is that you really understand it? Okay, let me take a look Mustafa, what the... So online participants are not saying anything that they understand everything. They figure out everything a while ago.
Yeah. 5 seconds delay.
Okay, but other than that, they understand everything. Okay. Because the one thing is clear, and that's the fact that, if I just add here vector that gets started from the origin of the body reference coordinate system and ends to origin of the body, could be the reference coordinate system and ends to origin of the body reference coordinate system, that's vector r. And if I add vector u bar there, that cannot be the same than where the position of this vector is. And why not? Because when the system is rotating, the vector u bar will go this direction. And it cannot be the case anymore. It just cannot. So what we need to do then is that we need to build this relation. And it's pretty simple mathematics. And that's what we're going to do next. All right? So the mathematics goes this way. Now, there is no body visible here. I only have here 2 coordinate systems, reference coordinate system and the body reference coordinate system. Let's call it global coordinate system and local coordinate system for sake of simplicity. This is my global coordinate system, and this is my local coordinate system. And you see that the local coordinate system is rotated with respect to global coordinate system amount that is theta here. And then there's a vector described with respect to local coordinate system. And the vector is vector u bar here. And vector u bar, it is having the angle with respect to local x-axis, which is equal than alpha. All right? What we need to do then is that we need to take a look at how is a projection of this guy, vector u bar, with respect to global x and global y-axis. Because that's what we need. That's what we are after. We need to know how it looked like with respect to reference coordinate system. Okay, so the projection in x direction is this one here. How can I know the values for this x direction? I know it if I sum up this theta and alpha. And if I do that, then it's pretty simple. You know it already. So it's length of vector u bar multiplied by cosine alpha plus theta. Okay? Alpha plus theta. What about this projection here? This y projection. Okay, again, I'm going to have a length. These are scalar quantities. You understand that these are scalars. This guy was a vector, but I'm looking at the length. So it becomes to be scalar as well. All right? So I have here y projection here is all the time same, except that instead of using cosine, I'm using sine. All right? And again here, angles are alpha plus theta. Then I will go my math book, and I check out the trigonometric relation that is shown here. Don't ask where I get it. Or you can ask, and the answer is from the book, from the math book. All right, so it's coming from the math book. So now using this relation, no thinking whatsoever. Remember, this course is not about thinking. As soon as you start thinking, you go wrong. You just go mechanically, okay? So I'm using this relation, and I can write this projection x and y as it is shown here. Now I can see that it's a little bit of motion like this. So it's no longer just this. Okay, hold on. That all becomes to be clear in my next slide. You want to see it? Okay, it's this one here. Okay, so this is what I just got from the previous slide. And I got that with no thinking. I was just using this trigonometric relation, nothing else. Okay. Then, if I think about how is a projection of vector u bar x, which is this vector u bar, with respect to local x-axis, how can I write that? Well, this is pretty much the same thing that I just did. So it's a length of vector u bar multiplied by cosine alpha. This time just alpha because remember I'm here in my local coordinate system. And then I could do the same for a y component. So it's a length of that vector multiplied by sine alpha. All right. So when I'm using that relation, when I'm substituting that relation to this previous equation, I can express everything as it is shown here. We become to be very close to solving the mysterious about two different coordinate systems. Because if you look at this coordinate or this solution here, this I have here two equations which I can express by using vectors and matrix. What are these vectors? Well, these vectors are representation in a global coordinate system, this guy, and representation in a local coordinate system, and something that converts local to be global. This magic, mapping, they call it mapping in mathematics, is our 2x2 rotation matrix. 2x2 rotation matrix, which is doing the trick for us. So it's converting vector u bar to be vector u. U bar, u. This, okay, let me show that in details. This is it. So this here is 2x2 matrix, which is orthogonal matrix. So what that means? It means that if you form vectors out of the columns of the matrix, those vectors are perpendicular with respect to each other. Perpendicular means that they, here in a planar case, they have 90 degrees of angle with respect to them. They could be matrix in n-dimensional space, which is orthogonal. And I cannot explain how it looked like. Just cannot. Leave it at that for mathematicians. Okay, so this is my rotation matrix. And if you look at the columns of this matrix, this column here actually is a representation of local x-coordinate axis. And this one here is a representation of local y-coordinate axis. That's why there are 90 degrees of angle with respect to each other. And that's why it is called orthogonal. They're also unit in a length, which is another benefit. But we are not going to really deal with that benefits too much. But it's orthogonal. All right? So what is the deal with orthogonal matrix? You know, why that it is so nice, particularly in our case? Well, it's pretty nice because, you know, sometimes we need to invert matrix, meaning we need to take this mathematical operation, which is a big pain typically, really big pain. But in our case, that is equal than transpose of the matrix. That means that we're changing the mapping direction from global to local, which we're really not going to use that much, but it's a possibility. Okay, so this is it. So this is the entire kinematics. We can repeat this more than 1 million times. Okay, let me come down a bit. So it's less than 1 million, but many times. We will use this kinematics over and over and over again. Okay, let's take a look. Here is my reference coordinate system. Here is my potato-shaped body. Here is my local coordinate system. And here's my particle. I want to describe this particle with respect to my reference coordinate system. First thing that I do is that I travel from origin of my reference coordinate system to origin of my local coordinate system. And I do that with help of this guy here. This is a vector that consists of two components. These components are projection in x and y direction, like we did in the case of single particle. But this time it goes to coordinate system instead of a particle. All right? Then I'm going to take the orientation of the body into account. How I will do that? With help of this mysterious mapping matrix, which is called rotation matrix. Okay, this guy here. And then I'm describing the particle using vector u bar. And it tells me where that is located. So this one here is R, AP. And this one here is a rotation. This is a vector u bar. Just testing out how long you can be quiet. It's pretty long. Okay, so how you say? What do you say? Pretty clear. Okay, so let me tell you something. A week ago, there was a university party. And in that party, I got the certificate that I've been a professor in this university 20 years, 20 years. I've been dealing with this thing more than that, way more than that, 35 years. And still every now and then I'm like, what is this? Like how this comes, how it goes. And when I'm explaining to you guys, it becomes clear like, just like that. You guys are with the very big brains. Nice, very nice. But no doubts, no questions, everything clear. Okay, most of our online participants, no doubts? Oh, that's not a question. Okay, so we continue then. Let's practice. Okay, this is comes with a little bit of small font, but I think that other than that is clear. So I have here a beam-like body. Okay, beam-like body. I'm asking where a particle that is located at the end of the beam-like body is with respect to reference coordinate system when the configuration is as shown in this figure. Information is provided. Only thing needed is that I need to substitute the information in the right location and do the math. Nothing else. Okay, so let's get started. So first thing, I need to look at this equation. And I need to substitute components correctly to this equation. What was the first component? What was this one here? This was where is that the local coordinate system is located with respect to global. That's what it is. Is that information offered? Yes, it is. So it's 2 in x direction, 1 in a y direction. That's it. Then I need to know what is the orientation of the body with respect to global coordinate system. That's angle theta. Do I know angle theta? Yes, it's p divided by 2, 90 degrees. Okay, that is then substituted to here, these 4 locations. And then comes the difficult thing, vector u bar. Okay? We know here, so we in this location, we are already oriented along the length of this beam-like body. So our x-axis is pointing this direction, okay? Y-axis is pointing this direction. How can I reach this this destination here, which is a point P or particle P. How can I go there? How much I need to travel in x direction? The length is, by the way, provided as a 1 meter is this direction. Okay, that's one. How much I need to travel this direction? 0. 0. Correct. That's 0. It is 0. I want to make you feel like, what the heck? That reading here is 0, and it is 0. And you do the math, that's it. Simple like that. It's a matter of substitution. You can play as much as you want with this equation, but you are not allowed to change this kinematics. You just cannot do that because this is a foundation, and everything is built top of this foundation. If you decided that, actually, I'm no longer happy with this foundation, but I want to build my house here, it will collapse. You're not allowed to do that. So you have to stick with this. So this is a kinematic we're using. There are other types of ways to describe these particles, but we are using this one. Okay? All right. Next example. Very simple too. So it's a beam-like body. And now the beam-like body, the body local coordinate system, the body reference coordinate system is located in the middle of the bar. By the way, in multibody system dynamics, where is that we can place the body reference coordinate system, the local coordinate system? We can place that anywhere we want. Sometimes it is beneficial to place it in the center of the mass. Sometimes it's not beneficial. Sometimes it can be within the boundaries of the body. Sometimes it can be out of the boundaries of the body. It depends so heavily on your application. But we are not limiting ourselves to any specific way where to put the local coordinate system, body reference coordinate system. Okay, here's my next example. Now this time the length of the body is 2. All right? This is 2. And again, the information is provided. So translation between the local and global coordinate system is vector 1, 1, which I'm going to substitute it here. Rotation of the body reference coordinate system is provided 2, and it is 3 multiplied by phi divided by 4. All right? That will go here. Then my vector u bar. Okay. Again, put yourself in a position of local coordinate system. So you here, and put yourself in the orientation of the body reference coordinate system, this local coordinate system. Your nose, meaning x-axis, is pointing this direction. Your y-coordinate axis is pointing this direction. How much you have to travel to go here? From here to here. That's going to be obviously length of the body. That's 1, but minus direction. Why? Because x is pointing opposite direction. Okay, so it's minus 1. How much I need to move this direction? 0, because I'm already in my body reference coordinate system. Okay, that's 0. The rest is downhill. Just symbolic math tool, and that's it. All you need. Okay.
I have a question. The local body system, you said we can place it anywhere and any direction.
Correct.
If we placed it the other way, would it be 1 then, or not minus
Yeah,
1?
it will be 1.
Yeah.
The only thing you cannot do is that once you have made this decision, there is no way back. There is no return. So you have to stick with this decision rest of your life. So it's a big decision. Yes, sir. Why? So you are saying that this one here is equal to 0. That's what you're wondering. Okay, so for online participants, the question is that, why this is equal to 0? The answer is because we are now putting ourselves in a position of the local coordinate system in the same orientation than the local coordinate system. So forget about the rest and put yourself in that coordinate system. So in that coordinate system, you should not travel at all transverse direction. You need to stay in a line of x-axis. That's what it is. Things would be different if I would be in this kind of body. Now here, if I would have a body reference coordinate system here, and my particle would be here, it would be a completely different story. There's a question, is there?
Yes, 2.
2. Oh my God. Okay, so it's a pretty small font. So can you define, so there is a question online from online participant, can you set the positive directions? And this was the same question that came from the audience. Yes, you can. In the beginning, you can place and orientate your body coordinate system however you want. Except in a written exam, you cannot. Because I'm going to give it to you and you just need to follow my whatever I'm thinking. Okay? But if you do the modeling by yourself, you can place it however you want. But you cannot change that once you have made your decision. You need to be consistent. Consistency is another. So mechanical, consistency. Those are the words that I keep on repeating. I also keep on repeating very, very, very important. Because everything that I'm explaining, I feel that is very, very, very important. Once I made a competition, like how many times per lecture I mentioned very important. And it is a lot. Okay.
The other one was about, can you please repeat how we got U bar?
Okay, we'll do that. So the question is how we can get the U bar. Okay, vector U bar is a kind of the mysterious component. So it's like good friend, at the same time is a little bit strange. Why? Because what the U bar is doing for you, it is defining a particle with respect to body coordinate system. Okay, let's take a look at the box-like body. This is a planar body. And I wanted to define the particle that is located here, this one here. And I'm placing my local coordinate system to one of the corners of this box-like body, lower left corner to be more specific. How can I do that then by using this vector U-bar? Well, the vector U-bar travels here to here. And it would be completely different. This, by the way, goes back to your question too. If I'm going to place my body reference coordinate system to center of the mass of the body. Now the vector U-bar will be very different. Why this vector U-bar is weird? It's weird because remember there's an infinite number of particles. And I want describing one. What if I would like to describe more than a one? This vector U-bar will do the job by scanning every single particle within the boundaries of the body. How it happens? Because this is a continuous system. We are not going to sum up all these particles because that will take too much time for us. Simply too much. Because remember, there's millions and billions and what comes of the billions? Trillions. What comes of the trillion? Many particles anyways. So we cannot sum them up, but we can use integration. And that's how we're going to do it. That's how we're going to take all these particles into account. So we're going to scan every single particle by using integrals, which I will explain you later, not today, but later. Okay. Mustafa, was that explanation good enough? You were not listening to me.
This is my second time.
Okay.
I couldn't prepare for
All right. Okay. So we can get back to that. Roll out the rotation matrix. And now I'm going to take a look at the success rate of the previous in-class quiz, but this is a new one. So let's take a look at the new one. And alternatives are describe the rotation of the particle. Now be very careful and please communicate with your fellow student what that is doing for you. Is that it describing the rotation of the particle? Remember what I said about the particle. Remember this. Remember, what is the role of, or how the particle is related to rotation. Try to memorize that. Okay, that's the first thing. Maps the body reference coordinate system and the global coordinate system. So it's mapping two different coordinate systems. Okay, maps the body translation and rotation. So maps the translation and rotation. Describe the translation of body A. One only is correct, but which one is correct? And how much is the success rate? Go and discuss. Discuss. You can come and discuss with me. No, you cannot because you end up to be in a YouTube. But I can step aside and we can discuss. No, you don't want to be my friend. Oh,
I believe it's gonna be an 8.
hey, that's always my favorite.
I know.
Okay, all right. So now you think this, and I'm gonna go to Socrates. Just a second. Uh, discard. Okay. This is scary thing. Hopefully everything goes correctly. Okay. Success rate of the first in-class quiz is this. Not a multi-body system. Is it going to be 100%? And if it's going to be 100%, we'll see. Ooh, I was about this close to say that if it's going to be 100%, I'm going to dance. It's you don't see it. It's a 95%. You need to be online to see this. So it's 95%. I will show that to you momentarily. You can check that out later. 95%. We got the winner too. We are not going to announce any names here, but we got the winner too. Congratulations. 96. Congratulations for the winner. And the next one is this one. Okay, role of the translation matrix. Oh, you don't see this at all. So, okay, let me go back. I will leave you to think about this. And now I need to think about how was the thing. I think of first this, then this, and then P duplicate. Okay, so 95 was correct success rate. All right, is it going to be 100% this time? For sure not. Absolutely not going to be 100%. But how low we go? How low we go? So what is your estimate? 90%. 70. 70 is pretty low. But this is difficult because the way that I made all these things to make you confused about the rotation of particles and all that, you're thinking like, what? What is the correct answer? But online participants use this WhatsApp to communicate because I really would like to see 100%. And we're going to take a still picture. I'm going to send that to Rector. Look at me. Best teacher ever. Okay, so we go. All right, then I have a short story here. Oh, I see that it's already 5 minutes past 5 o'clock. Would you like to have a break? You would like to have a break? Okay. How much? And 2 hours is not a good answer. How much you would like to have? 10 minutes. Okay, so 10 minutes break. I am not going to break the recording and I'm not going to break the streaming. 10 minutes and we will be back at 5:15. All right? Okay, now it seems to work pretty well.
Yeah, everything is fine.
The green screen is okay. It's not perfect, but it's okay.
Yes.
Definitely. Definitely. This goes to YouTube, so should we do it
I know.
later? So we can do it right after this one.
Okay.
So once we cut the streaming.
Yes.
Okay. I should actually have a slides which says break. We are on a break.
Yeah. Because I remember last year we had the break just for the first session. After that, you said that okay, no break, and then we said yes.
It's okay. We can have a break too. I think it is more, particularly those ones that are sitting here, is more pleasant this way.
Yeah, because you didn't know what they were doing behind their screen.
Yeah, that's right. That's absolutely right. Okay, so let me take a look what they say about this in these comments. 10% success rate. Completely feel the same. Okay, so we continue in 3 minutes. 3 minutes. Exactly. You're absolutely right about that. Mustafa, you need to. What was these weird notations? Theta is the one in the middle, but what is the first one? Psi. Psi.
The first one is
Phi.
phi.
Then the final one is psi.
Psi.
Okay.
Psi psi.
Psi.
Yes. Phi theta.
I think I should change this notation to be alpha, beta, and something simple than that. Something like that. So because I always struggle.
Yeah.
Phi,
Especially the last one. Phi
phi,
theta
phi,
and psi.
psi. Okay, I think you need to explain that to me one more time when we're in that slide. Hey, what do you say? Can we go again? Okay. So I don't know what would be a good way to get started. Should we first take a look at the in-class quiz? Okay, so let me, because I would like to show this how it look in Socrative in a same way that online participants can see it. Uh, you don't see this at all. So just a second, I will p duplicate. Still not. Okay, extend. Oh, you can see it. Okay, here it goes. So this is my screen. Okay, roll up the rotation matrix. Here it comes. So what is the correct solution? What is the correct answer? Out of the four, only one is correct. Which one is correct? Remember, we speak quite a bit about the mapping. We speak quite a bit about the rotation of the particle. Did we? Okay, so I think we can narrow down ourselves to two choices: rotation of the particle or mapping between the two coordinate systems. How was rotation of the particle? Non-existing. Non-existing. That's the same thing that the urban myth. So it's like a Santa Claus. Okay? Remember this. In many in-class quizzes from this on, I'm saying that one of the options is rotation of the particle. It was incorrect today, and it will be incorrect from any in-class quizzes from this on. Why? Because particles do not rotate. Whatever you vote, please do not vote that because it's like it hurts me physically to see that. And this time, oh, it hurts me big time, very much. I need. So please do not select that. You can select whatever you want, and I'm smiling. I'm happy. But if you're selecting rotation of the particles, I'm crying. I'm crying. I don't know if you want to make me feel sad. That would be the way to go. And see me in a corridor to say, "Hey, how is the rotation of the particle today?" And I'm gonna cry again. So no rotation. Remember that?
Yes.
Okay. We go back to. Hold on. I need to sit down to see this well. Oh, so the success rate was oh my God, 55%.
Almost that.
That's very low. That's very, very low. Okay, so we're gonna go back to the slide number 1 today, and we will start all over again. Okay, we will not. But remember, it's all about the mapping, two coordinate systems, and it's not about the rotation of the particle, not about that. It's confusing because body rotates, particle will not. Okay? All right, okay, let me take myself back to this one. Uh, ah, no, I don't want to use this screen, so just a second, I need to take this off. This is weird that I need to use this sequence to connect myself. Okay, not yet. Duplicate. Here it goes. Okay, okay. Short story. This I will keep this short because we have a long way to go today. So we still need to discuss about velocity and acceleration and all that. So, but short story about what about spatial case? What about three-dimensional case? How we can do the rotation and how we can describe the particle in the case of spatial system. We can do that in exactly same way as in a case of planar system. So no difference whatsoever. But of course there's a difference. And how it is different? It's different because dimensions will be different, of course. Vector R, which is this guy here, this one here, will have a projection along the three axes. No longer along the two axes, but three. And those are X, Y, and Z. That's why this vector consists of how many components?
Three.
Correct, three components. Three components. What about the rotation matrix? Rotation matrix will be 3 by 3 rotation matrix. Vector U bar, how many components? Three components. All right, so that's the only difference. There is a big problem here. And the big problem is this guy. This is a true problem maker. Very difficult component because this is rotations in a three-dimensional space. And there are books. People devoted their life to figure out what is the mystery about these rotations in three-dimensional space. Not yet solved. Why? Because mathematically, it is amazingly difficult to describe rotations in three-dimensional space. It comes with the complications which are related to computational mechanics, not so much about the real life, but how you do that mathematically. And these problems are the fact that there's no description that is superior at the moment. There are many good ones, but no superior ones. And if you go to the library, I don't know about library, but Amazon.com, and you type rotations and quaternions, which is related to this subject matter, there are many books. Books. Books about this single simple thing. And yes, it is. Not because of the mechanical engineering so much, but aerospace engineering. Big problem in aerospace engineering. And there's a lot of stories about this and that. And we are not going to take a look at all those, but just shortly, how you can do the rotations in three-dimensional space. There are many, many ways to make it happen. Now we're going to look just one, which is called Euler angles. Euler angles. Have you ever heard about that? No. You have. Oh, you knew you haven't. Okay, so Euler angles is the one way to make it happen. So it's based on successive rotations, meaning that there's a rotation after a rotation. So that's a successive rotation. So it's based on that concept. All right. So let's take a look. So the best way to describe Euler angles is by using two coordinate systems that are initially parallel with respect to each other. Okay. What I will do then is that I will take a hold of z-axis here, and I will introduce amount of rotation that is phi. Phi. Remember in one of those famous theaters, there is somebody that is whispering if you don't remember what to say. I have it too. No, that's Mustafa. When I don't remember, because I don't know, for some reason these weird letters are too complicated for me. So what was this again? Phi. Phi. Amount of rotation, which is a phi. Okay? That takes place around z-axis. Okay? So then I have rotated coordinate system. And I'm going to introduce a second coordinate, second rotation, which this time is amount of theta. That I remember. Theta. This time the rotation is along x-axis. Once rotated x-axis to be more specific. Okay? Then I'm going to take a look at my 2 times rotated coordinate system. I'm going to introduce one more rotation, which is psi. Psi. How come it can be that difficult? Why don't they use a simple name than that? Okay, anyways, again, around z coordinate axis. Okay? And now, before you say, and hey, you made a mistake. You made a mistake because, of course, it should be x, y, z. And where this z, x, z is coming from, did you make a mistake? This is one choice. Very often used choice, by the way. Very often used. And I've been wondering why it is so often used. Maybe because of the gyro. Because if you look at the gyro, here's in the upper upper right corner of the slide, there's a gyro. Not the latest model, but the gyro anyways. You look at the first axis, can be considered as a z-coordinate axis. Then x-coordinate axis, again the z-coordinate axis. And you can put the gyro any orientation in the space you want. You can make it happen. There's a problem. And the problem is already what you can see here. It could be the case that two gyro axes are in the same line. So they are perpendicular, they are parallel with respect to each other. And then you cannot differentiate what is what. And this is called gimbal locking. Gimbal locking. And there's a lot of stories about the gimbal locking, which is not locking, but inability to describe rotations in three-dimensional space. That's what it is. Always when you're using three components, you have this problem. Okay, let me take this back a little bit. There are some other promising techniques where it's not that serious problem anymore. But generally speaking, when you're using three rotation parameters, you will have this mathematical difficulty. Inability to describe rotation in a certain configuration. That's what it is. Then how you can get rid of that? By adding more. And adding more means that most of the modern computers, they are not using three rotational parameters, but four. Four? How come? Because as far as I know, body can rotate three different ways. So where the four is coming from? This four is coming from the fact that these four are not independent, but they are related to each other. There is a relation that combines these four parameters together. That's what it is possible to do it. Those ones often are called quaternions, which we are not going to touch this class. Will be later. All right. So, so the sequence we just look at. Now, listen what I'm saying. Put everything aside. And online participant, close Netflix or whatever you're doing in your other eye. So listen to me. So we use a sequence which is Z, X, Z, coming from the gyro. Okay? Z, X, Z. Clear. All right, so let's continue then. This is how it works. So we have these three rotations, and you can put your body or your box any orientation you want. And one more note here. So what kind of coordinate system we're using? Are we using left-hand or right-hand coordinate system? I know that there is a lot of differences there, but for some reason, I'm a big fan of this right-hand coordinate system. And if you see some of the figures in my YouTube channel, I'm using this. This means coordinate system. This is a positive rotation. And I also like gangster rap very much. So next time we see, this will be the way to say hello to me. But don't say hello, but say respect. Okay, respect. How you like that? So a lot of respect. Okay, okay. Let's get back to the real deal. But that would make me feel very, very good. And remember what make me feel very, very bad? Ask about how is my particles doing in a rotation wise. I'm not gonna like that. Okay, so here it comes. So what we can do to make this mathematical expression. Okay, so each one of these rotations we can describe by using 3 by 3 rotation matrix, which by the way is something that we are kind of familiar with, because first rotation, remember, that's along z coordinate axis. All right, so it's meaning that the last column here will be z coordinate axis. If you look at what is a submatrix which is located upper left corner of this 3 by 3 matrix, you already know that. That's something that you learn in the case of planar system. Second one, x-axis. So the first column, x-axis, 2 by 2, something you already know. Now located this time lower right corner. And one more time, x-axis. Look at the difference between this one and this one is that I'm using this phi and Mustafa, help me. Phi and what? Psi. Phi and psi. Psi. You read it. I don't need to pronounce that. You just read it there from my slides. Okay, so that's it. Now, successive rotations, which I said that is like the way to go here. How you take care of their successive rotations in mechanics by multiplying matrices together. Okay, let's multiply. So let me see. When I'm multiplying these matrices together, this is what I will get as a result. Okay, and now you're terrified, like, oh my God, do I need to memorize this? And the answer is no, don't do that. But memorize the concept, memorize the story, how you end up to have it. That I'm expecting you to know. But not that, and also, written exam, you're allowed to use all material, lecture note included. Okay, so that's how it goes. So that's my 3 by 3 rotation matrix, which is based on 3 parameters, Euler angles. So that's how it goes. Okay, so remember why I was repeating this number of times. What sequence we just look at? Was it x, y, z, z, y, x, z, y, z, z, x, z? This is testing your memory a little bit. Also, how well you listen to me. Okay, let me take myself back to, and again, for those ones that are in the lecture room, I need to apologize because this is going to break your view. Next. Okay, I will leave it, and I will get back to that momentarily. You see nothing. Okay. need to do this. And please communicate. And please make friends. Because you can go there and ask from these guys back there, like, okay, what do you think? What do you think? And you can always come to be my friend. Okay. Okay, a little bit what I already explained to you. So I said already that rotation matrix is orthogonal. So meaning that inverse is same than transpose. That's pretty nice. What that means physically, it means that the mapping order will be changed. It will be switched. Okay. Then if that's the case, if you have a rotation transpose of the rotation matrix multiplied by rotation matrix, another way around, that's going to be identity matrix. Identity matrix is a matrix where diagonal components are equal to 1, rest are zeros. Okay, so then rotation order is something that you cannot change in three-dimensional space. Two-dimensional space, there's only one axis where the rotation takes place, so that makes no difference whatsoever. But in three-dimensional space, you cannot change the order of rotations. And by the way, the game is on too, so about the success rate. How much we gonna get the success rate in that in-class quiz? I don't know because I got the answers here, which is like 86. There's 100%. I always voting 100% because I trust you, big time. Always. Okay, finally, we're in lecture number 2, and I know that I very heavily left behind the schedule, but that's okay because next story is very simple. Like I say, it's just math. We really don't care about math in any other way than tool that helps us to do the work. But tool is not the main priority in this course. It's just assisting us, nothing else. Okay, so we're gonna get the velocity and acceleration. And like I say, we have description of particle. Velocity of particle you get by differentiating that with respect to time. No different. No, it's not very difficult at all. Okay, and how it goes. Let me see what they say about. There is a rotation of particle. Somebody is again saying rotation of the particle in that window. Not my friend, that's for sure. Okay, velocity. Like I say, we're gonna take the kinematics we learned a little while ago, and we're gonna differentiate that with respect to time. Okay, what is that we learned? This one. This is a description of particle. And once you differentiate that with respect to time, what are you gonna get? Okay? So the first one, you differentiate this vector r with respect to time. You will get something that is called translational velocity. Okay? Then the second component is a bit more complicated because now there's a two components. There's a rotation matrix and vector u-bar. So it means that you need to differentiate both of these components as it is shown here. First rotation matrix and then vector u-bar. But remember how much vector u-bar is changing as a function of time. It's not changing because it's constant. It's not describing particle motion with respect to local coordinate system. That's not possible because we're speaking about rigid bodies. That means that this last component will be deleted. So we can get rid of that. Only thing left is this guy here, which is called r dot, translational velocity. And something where I have here rotation matrix dots multiplied by vector u-bar. Obviously, this is something that I need to take a close look. How can I differentiate the rotation matrix with respect to time? And I need to use a little bit of mathematical skills. I need to use a chain rule of differentiation, and it's not going to be too difficult. Okay? So I'm going to take a look at this such the way that each one of these components in my 2 by 2 rotation matrix are differentiated with respect to time. I know that this angle theta is a function of time. So when I use that, I can get what it is mentioned here. So I'm differentiating these trigonometric functions. So cosine will be minus sine. Sine will be cosine, and so on and so forth. Well, these are the two choices. When I do that, this is what I get as a result. There is a theta dot. Theta dot is obviously angular velocity of what? Is it angular velocity of particle? Who is voting angular velocity of particle? No, it's not. Remember, particle do not rotate. And if it do not rotate, it do not have angular velocity either. No, it's not cancelled, but it's angular velocity of what? Body. Body, correct. It's a body. Because rotation do not rotate. No rotation of particle. Okay, so that's what it is. So I can write this whole thing like it is shown here. And I can call this guy here, which is, by the way, rotation matrix, which is rotated 90 degrees, p divided by 2 to positive direction. That's what it is. Okay? So I can call that as a, rotation matrix A sub index theta. I don't know what's a good name of that. But that's what it is called. And this is something that is angular velocity. Angular velocity. Okay. But obviously, angular velocity is with respect to this guy here. We're going to take a look at then graphically once we look at the accelerations. Okay, very mechanical mathematics. Do you make any thinking? Please do not, because just look at what I'm getting. I will do all the work for you, and you just sit down and that's it. Everything will be fine. This is our velocity. Two components, translational velocity and angular velocity of body reference coordinate system. That's what it is. Okay, let's continue then. Acceleration. Okay, so we need to do this mathematical manipulation one more time. So we're going to take this component, differentiate that with respect to time. We will get translational acceleration. Okay? R dot dot. That's what we're going to get. Then we have here three components. This is constant, so I don't need to care about that. But I do need to care about this guy and this guy. Using this same technique that I used previously, I can first differentiate the one in the middle, and it's going to read like this. So it's angular velocity multiplied by rotation matrix dot, not rotation matrix, but rotation matrix sub-index theta dot. How complicated is that? Easy to read, complicated to spell out. Okay, and then this one, when I'm differentiating this angular velocity, that's going to be angular acceleration. All right, now you need to trust me when I'm saying that this relation holds. So once you do this differentiation, and there is a details available in lecture notes. So if you do not trust me, take a look at the lecture notes. This component in the middle can be expressed as it is shown here. I have now three components. These three components are translational acceleration. Then there is acceleration that is quadratically related to angular velocity. I will explain that, the physical interpretation of that component to you very soon. And then there is a one component that is associated to angular acceleration. Okay, so many times I got the question, okay, all look good, but where is Coriolis acceleration? Is the Coriolis acceleration part of the game? It's not. By definition, Coriolis acceleration takes place if there is a motion in a rotating disk. Okay, let me make you a rotating disk. Here's a disk which is rotated to ground here. There's a revolute here, like this. And if I rotate this potato-shaped body, and if this particle could be moved with respect to the rotating body, I would experience Coriolis acceleration. But that's not the case here, because vector u bar is constant. Okay, sometimes people get confused and they think that because Coriolis acceleration due to the rotation of Earth. That's something we really don't use in the case of mechanics. It is true that when I'm walking here, I am experiencing certain level of acceleration due to the Coriolis effect, because I'm moving in planet Earth. And they said that sometimes students can feel it very, very strongly on Friday evenings. And you need to drink a lot of alcohol and then you feel it. And it makes you so confused that you're having a hard time to walk straight. I don't buy that, because the amount of acceleration you experience in that case is insignificant. But anyways, we don't speak about that. That's another story, which we're not going to touch here. It is needed in aerospace application, but we don't need it, because we speak about mechanics and mechanisms. Okay? So if you want to learn more about these Coriolis acceleration, take a look at these YouTube channels that are offered in this slide. But names of these acceleration components: translational acceleration, normal acceleration component, tangential acceleration component. Let's take a look how is that they are. Okay, this is this. This, by the way, is this the do dots? There is a do dots. Tangential acceleration component. Think about that system is rotated with respect to local coordinate system. So tangential acceleration component is pointing in a tangential direction of that rotation. Okay? This one here, normal acceleration component, which, by the way, you got by differentiating this vector. Well, let me go back here. Oh, yeah, it is correct. So it's there's along this line here, so you can get that as a function of quadratically to angular velocity. That's how it is. Those are the acceleration components. This was minus in a direction, so if you put minus, so it's pointing this direction. Okay? What we're going to do then, many lectures from today, is that we're going to create the equation of motion. An equation of motion, simply speaking, is this: external applied forces multiplied by mass and acceleration. So this will be substituted here, and we will get the equation of motion. Not now. We are not ready for that. That's too hard for us today. And next Monday too. But slowly we become to be strong enough that we can handle something like that. Not today. Okay? What do you say? Do you have let me ask you this. Do you still have can-do attitude? Very much so. Very much. All of you. Online participants, do they have can-do attitude? No sign. Okay. All right, then. All right, I see that I'm running out of the time, but okay, let me explain to you something very, very, very important. Though, please pay attention to me, because this is what you definitely need. The next story. And the next story is called Generalized coordinates. Story is very short, but extremely important, because so far we have described how is that we can do the description of particle. But we have to be able to identify variables. Remember, in the very beginning, we tried this case that we're describing each one of these particles using these vectors. And I said that we end up to have too many variables to describe the problem. And we cannot do it that way. What are the variables we now using? Because we have to have these variables. Variables are unknowns, something we're solving using either kinematic analysis or dynamic analysis. So what are the unknowns? So we need to go back to the kinematics, which is this one. Okay? So what are the unknowns? So if I know certain components, then I can tell what is the position and orientation of each particles in the system. And it's mentioned in this equation. So I need to now go slowly each one of these components in my equation and identify whether or not this component is a variable. Variable is something that can change its numerical values when the body is translating or rotating. Or it can be a combination of translation or rotation, but what are the variables? Okay? First component. This one that is describing the translation. So let's think about this body here, which is this potato-shaped body. No motion limitation. It can go anywhere it wants. So what about these two components that is associated to this vector R? Are they variables or not? Meaning yes or no. Can they change their numerical values or not? Okay, now obviously I got you guys confused. Okay, so let me go back. So we have this potato-shaped body here. By the way, it's so great that I'm finally back in the lecture room because I've been doing this already, 2 years, and I'm explaining, and I don't see your faces because when I see your faces, it's like terrified. Then I know, okay, now I need to slow down. I need to do it again. In this online, like these online participants, they don't look good. Okay, let's go back and let's take a look at this potato-shaped body. If I take this potato-shaped body from this particular configuration, I move that to right and up. I put it here. What that means in terms of these components. Are they now changing or are they still keeping constant? Changing, correct. They're changing. So it's meaning that they describe the body translation. Now this consists of two components. Are they both changing or just one? Both. Both can change because body can go X direction and Y direction. Both are changing. Meaning that this obviously is a variable. So it's something we must know to be able to identify where is the body translation and rotation, body configuration, in short. Okay, then comes this guy. There's one parameter associated with this 2x2 rotation matrix, which is angle theta. Is that a constant or variable? Okay, let me hypothetically give you a is what? You guys are voting variables. What about Team Finland, which is back there? What is Team Finland voting? No, let them speak. Let them speak. So, is it variable? It's variable, yes. Okay, so it's variable. Yes, it is variable, because because the body can rotate. It can rotate, and when it rotates, what happens to angle theta? It changes its numerical values. Simple like that. One more component left. Vector U bar. Okay. I don't know, what is your name of your team? Team Blue. Okay, blue team is saying constant, not variable. Team Finland is saying constant. It is constant. It is not changing its numerical value because we're dealing with rigid bodies. Okay, so now let's make a list of all the variables. Okay, so we figure out that this vector R, that is a variable. What that means for us, both components of this vector are variables. Rx Ry. One more, which is angle theta. If you know these three parameters, three variables, you know everything. Okay, not everything in a life, but you know where the body is located and what is its rotation. You know that. That's all we need to know in mechanics. Okay, if I have one body, I need three variables, which are called generalized coordinates. What if I will add another potato here? How many coordinates I need in that case? How many variables? I mean, in total. So if I have two bodies, each of them needs three variables. I need total of six variables to describe it. Six. What if I have 10 bodies? How many variables, how many generalized coordinates I need? 30, correct. That's how it goes. Very simple math. So it's always adding more and more variables. Okay, that's how it goes. Now, one body, three variables. Let me repeat this one more time because next in class quiz, I'm asking this thing. I need three variables that are Rx, Ry, and angle theta. Clear. Now do this. Okay? All right, this is a special case which I get back to that. Body A. How many is needed? And what are these components? Look at the number, and if the number doesn't match, you're in problems. Okay, let me take myself away from this one. Hold on, lecture room. I will get this back to you so you will see this momentarily. And that's where we're going to stop today. This is the last thing. Okay. All right, so I need to take myself to this one. Euler angle. So how is the success rate?
It's really good.
Pretty good, yeah.
100?
Above 90.
Above 90.
You know that we will never reach 100.
Okay, a year ago there was a big claim that I'm the one that intentionally answered incorrectly. You said that I'm not the one. It's all about you.
Yeah, I know who is in charge for that way.
Ooh, very high. I got scared because of this dancing and 100%. Ooh, close case. Close case. Okay, let's move on to the next one, which is generalized coordinates. And now you need to see them one more time. Let me show it to you. Here it is. Okay, let me see how this look for online participants. So the delay is something like, yeah, this looks pretty good. Okay, think about the number. Think about U bar, and you will go the right way. Is what? What are the variables for one single body? A lot of whispering here in a classroom. So somebody's voting D. D. B. Huh. No comments. I better me not to comment that.
You can comment.
So I can comment that. Okay. So there's one vote for particle rotation in online participant.
Yes.
I noticed that. But what is the correct one? We just discussed this. Just discussed. Okay, are you guys ready? Oh, let me go back. Can I take this off? This slide. Go back to the Socrates. 5 more minutes and then we'll be off. Okay, so let me take myself back here. Okay, so are you guys, did you already made a conclusion? Okay, not yet. Hmm. Okay, so are we ready now? So body A means one body. One body.
One body has
Okay, so okay, let me tell you this much. One body needs what? And the answer is one body needs love. That's not the answer. But what? What the one body needs?
three coordinates.
Correct, correct. So it must be the one that consists of three components. Which ones? Okay, so I'm gonna take myself this one here. So success rate today is I got 71. I think this is pretty much all the answers today. 71 answers. Success rate is how much?
97.
97. 97. How is the success rate? What are the votes here? Oh, that's you. 97. So I'm saying 100%. Ooh, it's close. What do you guys think? I'm not gonna dance in this year.
No,
No,
no.
I don't think so.
Did you dance last year?
No, never danced in
Yeah.
my career. Okay, but there's always this risk, and when I'm pressing that, so the results, I'm almost bit like, oh my god, because the red goes this far. It's like, oh my god, it's 100 this time. It's not 100. Okay, what is the correct one? So everybody needs not love, but three coordinate to describe it. Three coordinates. Okay, and then that means that the first one must be off. So it cannot be the correct one. Second one consists of three components, so it looks very good. And this C is having too many components, so completely off. D is not correct because vector U bar is what? Constant, not variable. Okay, so what is left is B. So remember this, everybody needs, you can say everybody needs love, and then plus three coordinate systems. That's the way to go. Okay, so we done for today, and we see you on. We're gonna see you on Monday, but you can see you will meet Suraj on whatever day you want to go to do your tutorials. Okay, so can do attitude, respect, this way. Very good. Okay, see you on Monday then.